Yeah, do self-grades.
So we did self-grades last year, and we decided to stop doing self-grades because no one really liked them last year. Yeah. Yeah. Yes. Oh. Oh, huh. Oh, shoot. Okay. Right. Okay. Sure. Huh. Maybe something like canceled out or something. Yeah, that's kind of stuff. Oh man. Huh. Yeah, that's pretty strange. So for those ones, it'll be just your grade on the auto grader. That's the final grade for those questions. Yeah. Oh. Yeah. If anything, I would just say something canceled out, and then you just got lucky. Yeah. Yeah. I would say that's probably it. Welcome back. All right.
Also, if it's 0.
What's up?
If omega cross Q is 0.
Oh yes, yeah.
Well, it doesn't check whether you have like the exact right answer, just that you have something that works.
So we just check it for a couple of test cases. I think that we'll just throw a random angle at it and see if we get the right one.
I actually had like the wrong Q, and it still worked. And then I realized that I fixed the Q, and I put the proper Q.
Okay, that's kind of funny. Yeah, maybe it was just testing a zero angle or something.
Are there gonna be like solutions for these so we can like check?
Yeah. So the solutions are being released on Ed usually 2 days after the program.
Yeah.
Yeah, for the coding questions, there might not be, but I know that they report the correct twists in these solutions. Yeah.
Yeah. That's the
we were originally going to do a surgery problem on the kinematics homework, and then I don't know, like we decided to save it for later instead, so it might come up on the dynamics somewhere. So we'll see. I think this is the fourth one because we had linear algebra was like the unofficial first one. Yeah. What's up? Yeah. So I just attached it to the reminder for the last post on Ed. Yeah. All right. I'll give you guys just a minute to set up, and then yeah, we can get started. Oh, thank you. No.
What does they sound like?
Yeah. So SA stands for Sangolda. So it's the village in Goa where my dad's side of my family is from. Yeah. But it's a Portuguese name because it's part of the Portuguese part of India. So, yeah. Alrighty, cool. So we should be good to get started for today. So I'll just start out with the agenda, what we're going to be talking about, and then we will get into the contents. All right, so we're going to start out by talking about the types of robot joints. Then after that, we're going to talk about the joint space of a robot. And once we have those two concepts down, we're going to finish it up by talking about the actual forward kinematics problem. Forward kinematics. Oh, can we beat it up? Move over here. Okay. All right, sweet. So, as always, just stop me anytime if you guys have any questions about what we're covering, or if you want me to read my handwriting as well, that's just as good of a question. So do let me know, and yeah, we'll just stop at any time. Just feel free to call out or raise your hand, whatever works. Just a quick note, I think like the course guide for next semester is going to be released soon, so I would encourage you guys to take 106B. It's a fun class. It's kind of different to this one. It's very like project based. Like there are 4 super big projects. They take like 40 to 60 hours each to finish. So it's a big time commitment, but you'll learn a lot about robotics. It's very controls focused as well. So there's a lot of good material on that if that's something that you guys are interested in. There were no exams and only 4 homeworks last semester, but it does use Ross. Yeah, should be good.
I'm getting all good reasons.
It's a great class, yeah. Alrighty, so let's start out by talking about the different types of robot joints. Okay. So last time, where did we leave off? So we did this whole discussion about screw motion. We talked about twists and all these different things. And we're finally ready at this point to actually start talking about robots for our robotics class, which is great. So we've done all of this legwork about these twists, these screws, everything like that. We're finally able to actually be able to apply that to robot motion. Gotten to that point in our development. So our first step in this is to be able to break robots down into a couple of basic different joints that are much easier to analyze than just taking the whole thing on at once. Okay, so let's talk a little bit about the different types of robot joints. So there are 3 basic types. 3 basic types of robot joints that we'll discuss. Okay, so the first one of these is a revolute joint. We're going to talk about what these mean in particular in just a sec. I'm just going to say their names right now and then what we're planning on doing. So first we have a revolute joint. Second up, what we have is a prismatic joint. Prismatic joint. And third, we have a screw joint. Okay, great. So we have these 3 basic joints. Now, what actually might be useful when we're talking about these? What are some essential pieces of information that we'd like to know? Well, last time we said that we can represent any rigid body motion using a twist, which we represented with this letter xi. Okay. Oh, yeah, sure. So a rigid body motion is just anything that preserves the length of your body and preserves the orientation between points. So if I take this pen and I move it over here, the length is still the same. These vectors are still oriented the same. Yeah, good question. All right. So we said that we could represent any rigid body motion using one of these twists, right? And these twists were these 6-dimensional vectors of the form, some velocity up there and some angular velocity down there, right? In R6. And what we said was that if we take the exponential of the hat map of this twist, we get a rigid body transformation, all right? So we get some g equals e to the xi hat times theta, where g is a rigid body transformation. And we call the set of all of these rigid body transformations SE3, all right? So today what we're going to talk about is what these twists are for each of these revolute joints, or excuse me, for each of these types of joints. And we're going to see how we can apply these twists to figure out the transformation for an entire robot arm. Okay, so let's start by talking about the first type of joint, which is a revolute joint. What does it look like? What's the twist corresponding to this joint? How do we use it? Okay, so let's take a look at an arm like this. So say we have an arm that looks a little bit like this. It's going to be our first joint. And I'm just going to draw them with these like little cylinders representing like a rotational joint, and these little like lines right here, which are just representing like the actual solid links to the robot. I'm going to draw this little arm at the end over here. So it's got this hand, right? And say that this part is able to rotate about this axis, angle theta. We have this axis omega over here, okay? And as this rotates, it traces out this purely circular path in space, okay? So what are we concerned with when we're talking about the motion of these joints? What do we want to know? Well, we want to understand where our hand of our robot arm right over here is going as we're moving this joint, right? So we can do that using a twist. So let's summarize what we've talked about right here. So what a revolute joint is it's a joint that corresponds to a purely rotational motion about some axis, okay? So purely rotational motion. Okay, so whenever we rotate this joint, everything that's attached to it is going to rotate with it. So if this entire joint was translating in space as well, it wouldn't be purely revolute, okay? You just have this rotation about this axis. So what we're concerned with is the motion of our little hand on the end over here. And this is called the end effector of the robot arm. Okay, so whenever you see end effector, that's just a fancy way of saying it's the end of our arm. It's what we're looking at, what we want to describe the motion of. Okay, so what's the twist corresponding to a revolute joint? Well, you might remember last time that we discussed that when we have a pure rotation, we can describe the twist as something in the form negative omega cross q and omega. Okay, so remember this first term was a component of velocity that results from rotation. Okay, so that's sort of the part of this twist that will give us a displacement in space whenever we're moving this arm. So if I move my arm from like here to over here, this negative omega cross q is going to be taking care of a little bit of that displacement. And this omega down here is our axis of rotation. Okay, has a magnitude of 1. And it's simply this axis in space that we're rotating around. So if I'm rotating about my pen over here, like swirling around there, this pen would be pointing in my axis of rotation. Okay, great. So when we end up using this twist in practice, what does that look like? So if we take the exponential of the hat map of this twist, root and multiply it by an angle theta, we get out some transformation g. What does this transform do? Well, this is the transformation of rotating about axis omega by angle theta. Okay, and if we represent our twist in the spatial frame, this transformation will simply apply to vectors and points in the spatial frame. Okay, so as long as we represent this point q and this vector omega in the spatial frame, this will be able to rotate vectors or points about this axis omega in the spatial frame. Okay, so this rotates points and vectors in the spatial frame. Yeah. So if we have some frame like down here, yeah, thanks for pointing that out. So if we have some frame down here, we say that the spatial frame is a frame that's always frozen in space, it's never moving. Okay, so that's opposed to something like a body fixed frame, which we could say attached to the joint of our robot right there, that's moving every time. So we want to represent this joint in the spatial frame, so we can get a very clear picture of where this point is going, like in a clearly defined space that's never moving. Yeah.
So when you want to use like that one point, I keep on forgetting like when we can use like 0.000.
Yeah.
Using like, is it like only when it's on the same? So if like the point that we're referencing, or the angle that we're referencing, is on the same, like I guess like the z-axis.
Yeah, sure.
Then like we can our reference point doesn't have to be like say L0 or L1 L5.
Mm-hmm.
Like we don't have to use like 005. We could use 000.
Yeah, that's a really good question actually. So I'll make a little bit of a sketch as to what that looks like, and then hopefully this will help clarify things. Okay, so if we have a robot with 2 joints like this, okay, and say that it's like attached to the wall right there. That's just what these little dashes mean. Attached here. And we have our first axis, omega 1. We're rotating by theta 1 about that. And then we have our second axis, omega 2, and we're rotating by theta 2 about that. So what I like to do usually is you could just trace out where this axis is going in space, right? You do the same one for this one right here. It's going all the way down. Now let's imagine that we have some sort of spatial frame right here, okay? So let's call that frame S, like XS, YS, and ZS. And we want to find the twist associated with these vectors in the spatial frame, okay? Like we want Xi1 and we want Xi2 in frame S. Okay, so since these are revolute joints, we know that Xi1 will be like negative omega 1 cross Q1 and omega 1. And Xi2 will be negative omega 2 cross Q2 and then omega 2. Okay, so what's important here is that we want these twists in the spatial frame, right? So what that means is that this Q1 and Q2, these are going to be in the spatial frame. So if we take a look at our first axis, right, we know that this dotted line down here is tracing out where this axis goes in space. And we see it just goes right through the origin of frame 0, okay? So for a really convenient point to choose, we could pick like Q1 equals 0, 0, 0. But when we take a look at our second axis, which is this other dotted line over here, we see that it doesn't actually go through the origin, right? Maybe the next most convenient point we could choose, like if this is length like L1 over here, maybe we could choose a point like Q2 equals 0, L1, 0. But since this axis is shifted all the way over here in the spatial frame, we can't take this point as going through the origin. So it just depends on where our axis is located in space.
So if we had a revolute, let's say W2
Yeah.
was oriented to like right, right?
Mhm.
So then like because it's oriented to the right and it's not going through like on the z-axis.
Yeah.
That point, say we had another length was like L0.
Sure.
Right. It would be like if it was to the right, that would be on like the up 1, 2. Yeah, it would be 0. It would be 0, L1, L1.
Yeah, like if we, so actually what's important to keep in mind here is that like this point is actually just any point on this axis. So we could equivalently like take like we had some other distance like L1 right there. Another choice of Q2 would be like 0, L1. Let me call that L2 actually. I realize I just double named these. L2. So 0, L1, L2. That would actually end up giving us the same exact cross product. Just because of the properties of the cross product in this case. So it doesn't really matter like which one we pick along this axis, just as long as it is on that axis.
Yeah.
Yeah.
I think I'm just got a little like confused with that. On the question 3, one of the joints was facing sideways.
Oh, right.
Where it was oriented in space was like 0, 5, 5, I think.
Oh, okay.
So like if like the
like if we had something like
it was like yeah
that.
like,
Okay, yeah.
not like going in the same like z direction as the first one.
Yeah, so then our axis would be passing through in that direction. So maybe a point that we could pick would be like that one right there.
So then it'd be like like 2 different lengths. Like
exactly.
Like the length from the spatial frame bottom to the top, right?
Yeah, so you would need like that dimension as well as
Plus
like that one.
one.
Yeah, something like that. Yeah, great. Yeah.
I think like what confused me the most was how we picked the Q to be on that axis, but then the omega we picked it to be the original.
Oh, yeah, that's a really good point. So the thing that is important to point out is that omega is a vector, all right? So this means that it is just a direction in space, a direction in space, while our point Q is a point. Okay, so Q is referring to a physical location in space, while omega is just that direction. So, yeah. Okay, great. Yeah, no worries. All right, cool. So, sure. Yeah.
In the homework, there was like the spatial frame, and then there was a frame T. I personally didn't do anything with T.
Okay.
Or what?
Yeah, so we're going to talk about what that T frame is a little bit later when we get to the forward kinematics section. But yeah, for now, we did quite a bit more in revolute joints than I was thinking we would do right now, which is good, which is why a lot of this extra stuff has popped up. But yeah, T will just refer to the frame that we have like attached to this right here. So T is just the frame that's moving with the hand as we're going around. Yeah. But we'll talk more about that a little bit later. Okay. All right, perfect. So that's our revolute joints. So in summary, we say that for a revolute joint, we can find a twist in the form of negative omega cross q, omega, and this joint is going to be something that is purely rotating in space, right? So if we do e to the xi hat theta for this revolute twist, xi revolute hat, this is going to give us a transformation of rotation about this axis. All right, so let's talk about the second type of joint, which is a prismatic joint. Okay, so whereas that first one that we were talking about, that was just a purely revolutional joint, right? It's just revolving around some axis. Prismatic joints is, the logical next step. So prismatic joint is going to be a purely translational joint. Okay, so what does this look like? This might be a little bit weird to visualize at first, but say we have like some thing like this. Put my drawing skills to the test here. Like that. And we have our hand on the end like that. All right. So let's say that this is actually able to like move like in and out of the cylinder over here, right? Like it moves forwards and it moves backwards. If it's able to move by like some distance theta just along this direction, then we say that this is a prismatic joint. Okay. So prismatic equals purely translational joint. Purely translational joint. Okay. So this might move, for example, to some other configuration, like over here. If we move this joint further out, or we could also move it like further in, right? Like this hand could be maybe over here instead. All right. So we're able to just move it back and forth along this direction in space. Okay, great. So what is the twist? Let me do it. Twist. All right. So you guys might remember from last time, or just from our discussion of screw motion, that for a purely translational rigid body motion, we can use the following twist. So xi translational will look like the following: v and 0. Okay. So we have a 0 down here in the place of that omega vector because no rotation occurs. And this v is just a unit vector pointing in the direction of translation. In the direction of translation. Okay. So for example, in this case right here, we're able to move back and forth along this axis. We could take our vector v to be the unit vector pointing over there. Okay. So whenever we see one of these purely translational joints, just remember our twist will be of this. Okay. So what this means is that if we want to form some rigid body transformation involving one of these translational or prismatic joints, as we say, if we do e to the xi translational hat times theta, what this will give us is a translation of distance theta. Just remember that when we're using these twist coordinates, we always use theta to refer to the amount of distance. So if we're using a prismatic joint, that's going to be like an actual linear distance in space. But if it's a revolute joint, that's going to be the angular distance that we're turning. Okay. So it's the translation of distance theta in direction v. All right. So do we have any questions about this prismatic joint here? Okay, cool. So the last one we're going to talk about is sort of a combination of these two. Okay. And this is called a screw joint. So you guys might remember that screw motion was something a little bit special, right? So it was a rotation about an axis omega followed by a translation along that same axis. Okay, so what does this mean in the context of robot motion? Why might this be useful? How does it come up? Well, let's take a look at an example and we'll sort of see what this looks like. All right, so I'm going to draw this right here. All right, cool. All right. So what we're going to have is every time we rotate this joint about this axis, right? So say we're rotating it this way, about this rotational axis omega, we're not only going to be rotating about that axis, but we're also going to be translating along that axis. So you can visualize this like a screw, right? We have these little screw threads that are going up there. And force this guy to move upwards if we're like rotating this direction, or downwards if we rotate the opposite direction. Okay. So if we're rotating about this axis, say we might move up as well. So this entire thing will be moving. Okay. And we have a special term for every sort of screw motion that relates the amount of translation to the amount of rotation. Right? So the ratio of translation to rotation is called pitch. Right? So we define the pitch of a screw to be the amount of distance we translate for the amount of angle that we rotate. Okay. So say, for example, we rotate by an angle pi, but we only move 1 meter. What would our pitch be? Well, our pitch would just be 1 meter divided by pi, so 1 over pi. Okay. So how do we describe the sort of twist that's associated with this motion? So when we were talking about, screws and twists and all this stuff, we ended up deriving this formula. It's called psi screw. And we said it was equal to negative omega cross q plus h times omega, where h is just that pitch that we just talked about. Okay, so that's going to be our velocity. And then on the bottom, we just have omega. All right. So just as a review, term by term of what this means, let me just highlight these here. So what this is this is the translation along axis omega. All right. Because this h is converting whatever theta we multiply this twist by into some sort of translation by a distance of d along this axis. Okay. And this negative omega cross q is just the translation from the rotational motion. Right? So you guys might recognize that negative omega cross q from the case of a purely revolute joint. Okay. So it's just like if I start over here and I rotate my arm over here, that negative omega cross q will be taking care of that part. And this h of omega will just be the amount that I move upwards along that axis. All right. So do we have any questions about this screw? Yeah.
I have a question, like for the first.
Oh, sure. Yeah.
So I was thinking, like, data is in terms of radians, right?
So in this case, theta is in units of meters here.
This is the.
Yeah. So for the case of a prismatic joint, theta is just referring to the amount that we translate along the joint. Yeah.
All right. Okay.
Sure. All right. So in this case, if we do a transformation of the form e to the psi hat screw times theta, and we get back some transformation g, what's this going to give us? Oh, yeah.
Do we have translation from the rotational? So do we have translation from both of them?
Yeah. So the first translation is like we're rotating about that axis. So it's like if I start my hand over here and I go over here, and then the second one is we translate along that axis like that. So it's just breaking it up into two parts. Right. So we have this G in Fe3, as always, right? So what does this give us? Well, first it gives us a rotation by angle theta along axis omega. And after that, what it's going to give us is a translation by the pitch times the angle that we move, right? Because that just gives us the distance along axis omega. All right, perfect. So that finishes up the main 3 types of robot joints, okay? So we have a revolute joint, which is what you guys have on like the Sawyer robots downstairs, if you messed around with those during lab. We also have prismatic joints, which are just these pure translations back and forth. And finally, we have these screw joints, which are a combination of the two. So do we have any questions about these 3 like fundamental joints for robots?
Can you think of a screw joint as like a combination of a revolute?
Yeah, absolutely. Yeah, so if you take a look at like this screw joint, it's actually just sum of a twist for a revolute and prismatic. So that's like equal to psi revolute plus psi prismatic. Yeah.
What do you have by translation by h theta along the axis omega?
Oh yeah, that's
the magnitude like the movement or something?
Yeah. So whenever we rotate like by an angle theta about here, the definition of the pitch for a screw is it's the ratio of the amount of like translation that occurs versus the amount of rotation. So if we're rotating by theta, we're going to end up translating by some distance, h times theta, right? Because h equals d over theta. So when we multiply h times theta, that just gives us like d over theta times theta, which gives us the distance d that we translate. Does that make sense?
Yeah, so it's like P rotate, sorry, your translation.
Yeah. Sure.
So when we compare that to the magnitude one,
Right. So omega is a unit vector and nothing else needs to be in this case.
Okay.
Yeah, that's a great point. All right. So, let's see, was that all that I wanted to talk about? All right, cool. So let's talk about how this sort of ties into the more general case of robot motion, right? Let's see how these might pop up in a practical problem that we're going to do. So say this is our first joint, this is our second joint of our robot arm, and then finally we end up with something like this all the way through. Okay, so say that this is an axis of rotation, this is an axis of rotation, so like theta 1 and theta 1, or theta 2, and then finally we have like theta 3 over here, okay? So if we take a look at this arm, what we find out is that this first joint, right, this is like a rotational joint, okay? So it's revolute. The second joint, we're also just rotating about this axis, right? So this is also just revolute. And this third joint over here is able to move up and down in this final location. Okay, so this is a prismatic joint. So we find that when we take a look at these more complex robot arms, we can really just break them down into these simpler joints that we know how to describe. Okay, so we now know what the transformation associated with a revolute joint is. We know the transformation for a prismatic joint, so on and so forth. So if we're able to break our more complex robots down into these simpler joints, we already know the transformations for those joints, then we're already well on our way to figuring out these problems. Okay, so let me just write that down right here. You know the transformations for each. Okay, great. So do we have any questions about this, just as like a summary of this whole thing that we've done? Otherwise, we'll talk about joint space for a little bit. Yeah. I can make it look hard if you want. Nice. Alrighty. Do we have any other questions? All right, cool. So let's talk about the joint space. Okay, so we've come up with our first like basic definition of what these robot arms are, right? Like we know these different types of joints, we know we can break them down into these simpler parts. Now we want to start getting a little bit more specific, a little bit more mathematical in how we're talking about this. Okay, so what we want to do is we want to figure out some way to write a set of all possible robot configurations. Right? Because this is kind of a handy way of looking at robots, right? Like if we have some convenient description of the set of all the different possible places this robot is able to go, then that's going to be kind of helpful just as like a first glance as what this robot is capable of, right? It might tell us how many degrees of freedom this robot has, right? Like how many parameters we can independently change, or which ones of those degrees of freedom are made revolute or prismatic, and so on and so forth. Okay, so we want to be able to try and figure out some mathematical way to write the set of all the different joint angles and all the different combinations of joint angles out. All right. So if we have some manipulator arm like this, I'm going to be drawing this guy a lot. Kind of looks like, I don't know, marshmallows on a stick or something.
No.
So we have our angle theta 1, theta 2, and theta 3. We're essentially asking the question, how do we describe the set of all combinations of joint angles. Okay, so say we start like in a straight out configuration, for example, right? Like all of our joint angles are 0. Now, if I just simply move one of those joint angles, say to like 45 degrees, then that's an entirely new configuration, right? Now I move this one, I got a new configuration again. So we want to be able to represent the set of all of these different possible combinations of these configurations on that. Hey, so how are we going to do this? Well, we're going to be able to describe, maybe the set of joint angles for each individual type of joint first. And then after that, we'll come up with a nice mathematical way of describing the set of combinations. Okay. So let's start out by thinking about sets of all possible joint positions. Joint positions for our basic joints. Okay. So we want to figure out, what the set of all possible positions for a revolute joint is, maybe what the set of all possible configurations for a prismatic joint is. What do those sets look like? What can we call them? All right. So let's talk about the revolute one first. Revolute. And once again, we'll just start out with a simple basic sketch. Make that a little more nicer. A basic sketch of what a revolute joint is. All right. So start out with something like that. And this guy, he's just able to revolve about this axis omega. And we describe its position on the circle by some angle theta, right? Like if we take a top-down view, what does that look like? So maybe we have, our axis over there, and the end of our arm over there. It's tracing out this nice circle as it goes around. This is our robot link. And say that this is at some angle theta on the circle. Well, what do we actually know about this angle theta, right? How can we describe the set of all possible angles theta for this joint to be at? Well, what do we know about theta? What do we know about theta? Well, the first thing is theta is just a real number, right? That's pretty basic. So theta, element r, right? We have no reason for our angle to be like a complex number. We know it could be either positive or negative. It could just keep spinning around there pretty happily. Well, we want to be a little bit more specific than that, okay? What else do we know about this angle theta? We know that after 2 pi, what's going to happen is this angle will start to repeat itself, right? So once theta crosses over 2 pi, right, it essentially just resets to 0, and we start describing the same configurations again, right? So after theta equals 2 pi, we start repeating joint positions. Okay, and that's something that we don't really want to do, right? So if we want to be really specific about the set of all possible configurations for this robot, it won't really be very convenient for us just to straight up use the set of real numbers, right? Because we know that after 2 pi, after 4 pi, 6 pi, so on and so forth, we're going to keep describing the same set of joint positions. So we really want to hone in on the fundamental set, okay? So if we just describe theta by the set 0 up to 2 pi, okay, so this means that we include 0 and that we go almost up to 2 pi, but we exclude the actual value of 2 pi itself. We'll be able to describe all the different positions of any revolute joint just using one of these, okay? So we give this set a special name. So special name for the set of revolute joint positions. Joint positions. And we call that set S1. Okay, let me just box that in right there. So what does S1 mean? Why do we use that? So S, I was looking earlier for like a translation of S, but the best that I found is that S just sounds like circle. You spell it like circle, something like that. Yeah. So S.
Is that the power point?
So it's not really a power, but it indicates the number of coordinates we need to describe our position on that circle. So we need one angle to describe position. Okay. So if we were like able to bump this up a dimension, for example, and we write S2, that actually describes a sphere, right? So you can think of like the first angle theta like being this angle over here, that angle theta, And then our second angle theta being like, so we have like that point, theta 2, like that angle right there. So that 2 is just referring to the number of values or angles we're going to need to figure out our position on that circle, which is why like 2 is a sphere. If you go up to 3, then it's like a 4D sphere. And so, okay, cool. So we give it this name S1 to describe the position of all of these joint angles, right? And the only reason we do that is that we don't want to repeat ourselves. We don't want to keep going on like 4 pi and 6 pi when we know it's just the same thing as being in the original position. Okay. So do we have any questions about that definition or why we needed it? Scroll back down. Okay. Sure. Great. I'll give you guys a second to copy that down. Okay, cool. So next up, we're going to talk about prismatic joints. Prismatic joints. So what is going to be the set of all possible configurations for a prismatic joint to be at? What's that going to look like? So in this case, we just redraw that one that we had from earlier. Right? We have this prismatic joint coming out here, and we have like a little arm over there. Okay, so we know that this prismatic joint is able to move like by some distance theta along this axis, right? It'll be able to go to any different position along that axis. So do we have the same restrictions as theta? So, or excuse me, as the revolute case. So what restrictions do we have? Well, let's think if we actually have any. So the first one is that we know theta will be a real number again, okay? So theta element R. But are there any other conditions that actually allow us to restrict the value of this distance? Well, when we're just thinking about moving on a line, if I move in a line that way, will I eventually reach this position, right? I know, like technically, if you go around the planet, you'll come back, but that's a revolute joint in that case. So if we're simply just traveling along a straight line, we're never actually going to repeat ourselves, right? So there are no restrictions on the value. Okay, so for that reason, we just use the set R to describe all the different possible positions for a prismatic joint. Okay, that's as specific as we can get. All right, great. So it turns out that just using these simple descriptions of rotational motion, like the set of all rotational motion values and the set of all translational motion values, we'll actually be able to figure out the set of all possible values for our robot arms to be at, whether they're using a screw joint or a revolute joint or a prismatic joint or some combination of all of those. Okay. So now we're going to come back to our example from earlier. Let me just copy and paste this right here. Scroll back down in just a sec. And let's go ahead and paste this down. So we have some different combination of joints over here. Oh, yeah. Sure. So our question now is, what is the set of all combinations of joint angles? Okay, so we already know that we're able to describe the set for each individual joint. Now we're just going to extend it to the whole thing. Okay, and just for the sake of this example, I'm going to change this last one over here to a prismatic joint, just so we see how that works. All right, so it's prismatic, and that's coming through there. That's able to move down. Okay. So I'm going to write this out at first, and then I'll just come back and explain what I've written afterwards. Okay, so we call this set Q. Call the set of all joint combinations Q. All right, and I'm going to write Q out as follows. So Q equals, for this robot arm above, it's going to be S1 cross S1 cross R. All right, so let me just talk about what's going on here. All right, so we know that S1 will correspond to a revolute joint, right? Like this is going to have the set S1 describing all the possible values. It's going to have S1, and this is a prismatic joint over here. So that's going to be described by R. Now, what this little cross does is it says, give me all of the combinations of these sets. So don't mix it up with a cross product. They use the same symbol for that. Oh, scroll. Sure. So they use the same symbol, but this is actually something called the Cartesian product. All right. Cartesian product. And if we take the Cartesian product of two sets, what's that? What that's going to give us back out is just the combination of all the values in those sets. All right.
So is Q the joint space?
Yeah. So Q is called the joint space. The joint space. All right. So we call this big set of all the different combinations of, theta 1, theta 2, and theta 3, the joint space of our robot, since it's describing the space of all possible joint positions. Yeah. So the workspace is a little bit different. So were you guys talking about that with inverse kinematics? Or, yeah. Yeah, a little bit. So you could use like the joint space to figure out like what your workspace is in some sense. Sure. All right, cool. So whenever you see this like set Q right here, and it's equal to like all the values of theta 1, like combination with all the values of theta 2, combination with all the values of theta 3, we could just refer to elements of the space Q just as a vector of these different distances, like stacked on top of each other. Okay, so we can call like some big position vector for our set like theta element Q, where theta is just going to equal each individual joint position, one on top of the other, right? Theta 1, theta 2, theta 3. And the reason for this is that each theta is just going to be one potential combination of the joint angle. Okay, so we just write it in this 3D vector for convenience. Now, if we had n joints, this would become an n-dimensional vector. All right, so we just write it in a vector for ease of use. Okay, and each vector is just one combination of joint position. Okay, great. So that's sort of what the joint space for this robot is. Just remember that we use this notation of the Cartesian product, this little cross sign, to denote the combination of all the values of these sets. All right, so do we have any questions about what we talked about here? Right. So it's not the cross product. So if you see like cross when applied to sets, it gives the combinations. But when you see cross applied to vectors, then it's a cross product. Yeah. Oh, which one? Like right here? Oh, yeah. Alrighty, cool. So let's see. Okay, great. So we're making pretty good time. I think we'll have time to do a few examples with forward kinematics, which is good. Are we ready to move on to forward kinematics, or how you guys feeling? Good. Nice. All right. So forward kinematics. Sorry, was anyone still copying stuff down up there? Okay. Like sometimes I'll scroll down, I'll hear someone like breathe in. I'll be like, oh no, go back. Oh, sorry, that's ease of use. Yeah, we just put in a vector to make it easy. Yeah. So we're going to talk about inverse kinematics next week, because I think you guys still have one more lecture on that.
So is it on your midterm?
It will be on the midterm, yeah. So I think they're releasing a homework at 5 today, which is on inverse kinematics. Yeah.
When's that due?
Believe it's next Tuesday. Yeah.
The
Midterm is Thursday. It's pretty short. I think there's only a couple problems on it, and there's no bonus as well. So it's pretty constrained.
Is that the midterm or is that the homework?
The homework is due Tuesday. The midterm's on Thursday.
Okay, and then you said the Thursday's short or the midterm's short or
Just study hard. The midterm will be short.
Tuesday's homework will be short, right?
I think it's on the shorter side for sure.
Okay.
Yeah, It might be like a little bit longer than the forward kinematics one, but yeah.
Do midterms and bonus questions for this class?
At the moment, we're not planning on having any bonus questions, but yeah, we'll
How
see.
involved would the lab questions be?
So the lab questions will be pretty similar to what there was in the practice one that was sent out. It was just like, what does your file structure look like in ROS? Or yeah, yeah. So that might be a good thing to like put in your cheat sheet.
Okay.
Yeah.
Okay, well, yeah.
Yeah.
Is the cheat sheet typed or does it have to be?
I believe it's handwritten. Yeah, but you could write it on like a that's fine if you do an iPad and then that's good. You know, I can make one and then send it out if you don't want to make a cheat sheet. but yeah, it's good to make one. I know it's kind of a pain. All right, so let's talk about forward kinematics, what it is, and why we want it. And yeah, so I think this is a pretty exciting point in the class. We're sort of moving away from some of that more abstract material on rotations, and we're actually starting to apply it to practical robotic systems. So it's a nice turning point. All right, so let's talk about our forward kinematics problem. So we have a robot that looks like this, our marshmallow robot, and we have our hand over here, and say that this is some omega 1, beta 1, and then we have omega 2 and theta 2. Okay, so here's our problem. What we want to do is figure out where the little hand on the end of our robot is. So where the hand is, we call that hand the end effector, remember? End effector. In terms of the joint angles. Okay, so in this case, we want to try and figure out both what the position and the orientation of our hand here at the end is, just based on this theta 1 and this theta 2. Okay, so we want to figure out some function that will map us from these angles into the actual position and orientation of this hand. So I'm going to write a little bit of setup for that, and then we'll sort of see how this problem will fall out of it. Okay, so let's say that we have a frame over here that is completely frozen, right? It's fixed at the base of the robot. Okay, I'm going to call that the spatial frame S, like XS, YS, and ZS. All right, so this is called the spatial frame, and it never moves. All right, so when you're working like in the lab in your robot, what might the spatial frame be? So it could be either the base of your robot, or it could simply be your perspective, right? Maybe you're just sitting there at your desk, you're watching where the robot's going, the perspective of your eyes looking at the robot. That could be the spatial frame. Okay. And then in addition to the spatial frame, we also need to have something keeping track of where this end effector is, right? So what we're going to say is we have this point, we have this other frame up here, and that's going to be called the tool frame, frame T, okay? And we're going to have like an XT, a YT, and a ZT, right? So this is the tool frame. All right, and this is rigidly attached to the hand at a certain point, all right? So it moves with the robot.
When you say hand, you mean the end effector?
That's right. Yeah.
You mean left hand or right?
Oh, so when I say hand, I just mean like this little guy over here, the little gripper at the end of the robot. Yeah. Yeah. So just like. Yeah. All right. Cool. So it moves with the end effector. Okay, so if I rotate it, say like this is something that's marking out my frame, we see that, this is just moving with my hand as it goes, but my actual shoulder is staying still, right? Like I could place a frame on my shoulder, that would be my spatial frame, and then I could place a frame like on my little pen over here, and that would be the tool frame in this case, okay? All right, so let's think about our problem right here. How can we keep track of the position and orientation of this tool frame with respect to the spatial frame, all right? So how to keep track of the position and orientation of the tool frame with respect to, I'm just going to write WRT for that, with respect to the spatial frame. All right, So this is sort of where all of our description of rigid body motion finally like comes to light, okay? So we know that each link in this robot is going to be rigid. So each link is rigid, all right? And when we move each link, we could describe that motion by a rigid body transformation, all right? So link motion equals rigid body transformation. All right, and we also know that we're able to compose rigid body transformations, right? Like I can compose a rotation of this part of my arm with this part and we get some total rotation, okay? So we can also compose rotations. Or compose rigid motions. All right, so what all of this information tells us is that we're able to figure out some sort of rigid body transformation between frame T and frame S for any choice of joint angle, all right? So we're able to figure out, we do this in a different color actually. So some transformation between these two frames. I'm going to call that transformation GST of theta, all right? So what is this GST of theta? Well, it's going to be a rigid body transformation in SE3. And what it's going to do is it's going to take a point in frame T and transform it to frame S. To frame S, okay? So why might this be useful? For example, like if we plug in the origin of our tool frame and we try to convert that into frame S, that'll tell us where our hand is in the spatial frame at all points in time, right? So using this, GST of theta, we have this really powerful ability to convert anything like in the moving frame of our robot into our world frame where we're sitting and where we want to be able to interpret these points, okay? All right.
Hi.
Oh, yeah.
Maybe a new question.
Sure.
Why do we assume that the frames are the same?
Oh, yeah, that's a good question. So what we want to do is just make this like as general as possible, right? So for example, some configuration of the robot could be like something entirely different like this. Now, this frame, which is our spatial frame, will always be staying still, right? But now this frame over here, frame T, has been like rotated by all of these joints, okay? So although it's still pointing in the upwards direction, maybe our X vector is like coming out here now, and our Y vector is pointing out there. Right. So the actual orientation of these vectors has changed, and also the position of this frame in space has changed. All right. So like the distance from here to here is now different, right? Like that's PST over there, and then the orientation, which is RST, is no longer the same. Yeah. So changes with theta 1 and theta 2, or those are our joint angles. Okay. So how do we do this, right? What's a really convenient way of figuring out how we get this transformation from here to here? Well, one way is, we know we can form these rigid body transformations using twists, right? We can form GST of theta using twists. And what we also know is that we know the twists for every simple robot joint, right? So what we could do is we could just find the transformation associated with each different joint in here. And then using those transformations, we'll be able to figure out where the end effector of our robot is going along. All right. So we can take this problem of finding this very complicated transformation and break it down into just finding these simple twists for each joint. Okay. So simplify this problem. Complex transformation into finding twists. All right, cool. So let me just write out formally what this map GST of theta is doing, okay? So formally, what it's going to give us is we're putting in some vector q, or excuse me, some vector theta, and what that vector theta will be is it'll be an element of the joint space q, right? Like it's going to be theta 1, theta 2, theta 3, so on and so forth, okay? So it's taking us from some element of our joint space, and it's giving us back out a rigid body transformation in SE3, okay? So takes in theta equals this vector, theta 1 through theta n. And it gives us back a rigid body transform between the spatial frame and the end effector frame. Yeah.
So on our homework last night, where we were at the parameter of all graded questions, that was essentially.
That was cute. Yeah. It's pretty cool. So Q is the joint space of your robot, right? So
No, like, what did you just say?
I was saying that, like, I was asking if the parameter of all three of the functions that we had
Oh, the theta?
was Q, yeah.
Okay, so theta was Q.
there's only one.
There was a
Right.
nothing.
So you're passing in like a vector for
There's
joint
an
angles.
element.
So
Q is itself a set.
It's a set.
so Q equals, like a set of joint angles.
Theta was only an L.
Right. So theta is one possible combination of joint angles.
But like, let's say Q is made up of multiple. In the homework, there was made up of multiple product, Cartesian products.
Right.
Yeah, and we just looked at one element. And then one element would, like, its length would be the number of products we took.
Would be the number of joints that you have. So like if you look at
Number of products plus one.
so I think it would just be the number of products if you just have purely revolute and prismatic joints. Yeah. So if you have like S1 cross S1 cross theta R, which is that one that we had earlier, we have like theta, like an angle theta 1, and angle theta 2, and like distance theta 3 in that case. So we would have like a vector like theta 1, theta 2, theta 3. Yeah.
What is the difference between SE3 and SO3? I know SO3 is like the transformation matrix. but I'm not
Yeah.
sure about SE3.
Yeah, so that's a good question. So SO3, excuse me, is just a rotation matrix.
That means it's orthonormal and has determinant plus or minus one.
Determinant of plus 1.
Plus
Yeah, so that's what that S stands for. Like special means determinant of plus 1. Yeah, so you have like R transpose R equals the identity, which is what you were saying.
Well, sometimes it's like -1 and +1. But in this class, I think the professor mentioned +1.
Yeah.
Lowercase messed up or something?
This is uppercase.
Okay.
Yeah, so we need that plus 1 to preserve the orientation between factors. All right.
Okay, yeah, that makes sense.
Cool. And then SE3 is the set of all rigid body transformations. Rigid body transformations.
And it's a 3x3 matrix, right?
So SE3 is going to be a 4x4 matrix. So we're going to have like an R, a P, a 0, and a 1. So where this R is actually a rotation matrix in SO3, it's going to be like a position vector in R3 that's telling us the amount we get to translate. And then this is going to be like a row of zeros and a 1.
It's a set of all rigid body transformations.
Yeah.
So it's multiple 4x4 matrix, right?
Mhm.
Then SO3, it's a set of 3x3 matrix.
Yeah, that's right. So 3x3 matrices, and this is going to be 4x4.
Is it just a rotation matrix? So just one matrix?
Just one matrix. Yeah. Yeah, so like you could think of SE3 as like we're plugging in different matrices and vectors to make this bigger transformation. All right. Do we have any other questions before we continue? Yeah.
So like, do you need to prove that R transpose R? Do you also need to prove that R transpose is equal to I, or is that just follow from that?
I believe in this case it should just actually, yeah, so if you assume it's a 3x3 matrix, then it should just follow from that. Because basically, like usually when you're talking about the inverse case, like R transpose R equals R transpose equals I, is making sure that your matrix is square. Because if you could do R transpose R and you could also do R transpose, then the number of columns has to be the same as the number of rows in the matrix. Sure.
Is there a lowercase SE3? What does that mean?
Yeah. So lowercase SE3 is the set of all psi hat twists. Okay, so when we're doing like B to the psi hat theta, the set of all the psi hats is going to be this lowercase SE3.
So would that be like a binary?
So not quite. So psi hat is going to be like a matrix of the form omega hat V 0, 0. Right, so that's going to be 4x4 matrix. And then the actual one that's 6-dimensional is Xi on its own, which is this vector.
So the ham mapping reduces the dimension in this case.
So no, sort of. So we're going from like this vector in R6 to this matrix in R4x4. So there are actually 16 elements in this matrix. Yeah. Right, great. Great. So let's talk about how we can use twists. Twists for robot kinematics. All right. So let's try and figure out this transformation GST of theta for the following robot. What does it mean? So I'm going to sketch out this robot with 3 joints, and then let me make this a little bit bigger actually. So we have our first joint over there, then that leads into our second joint, our third joint, and then finally we have our end effector over here. All right, so this is our end effector. All right. And just in this case, I'm gonna just draw these out as revolute joints, but just remember that these joints that I'm choosing are actually entirely arbitrary. So I'm just gonna deal with them in terms of the twists, but just for the sake of visualization, I'm just gonna sketch them as revolute joints, right? So we're gonna have some twist Xi1 and some distance theta1. Now I'm going to have some twist Xi2 and some theta2, some Xi3, and a theta3, all right? So here's what we're going to try and do, all right? What we're going to do is we're going to try and figure out this transform from our frame S over here and our frame T over here, all right? So how do we go about doing this? What's our process going to be like? All right, well, to sort of think about this and sort of get a starting point, what we're going to do is think about GST of theta. So what is GST of theta doing? Well, let's imagine that we have some point in the space T over here. All right, I'm going to call this PT. And this is a point in space that's currently represented in frame T. So based on the definition of GST of theta, this map should be able to give us transformation from PT to PS. Okay, so if we multiply GST of theta by a point in frame T, we should get back that point in frame S. All right, and this should be true for any joint angles. All right, so say our end effector is like at some other position, maybe it's like over here instead, and our point is now pointing over here. We want to be able to find that transformation between those for these other configurations as well. All right, so this transformation GST of theta should always give us a map between our point PT and PS. All right, so it takes our tool frame point, and it gives us back that point in the spatial frame. So what does that actually look like in this case? Well, what this is going to be is just like this big vector over here. Let me draw it a little bit straighter, actually. Okay, cool. So if PT is that point up there, then PS is going to be that one, right? Because it looks super far away from the spatial frame, even though it looks like it's right there in this tool frame. Okay. So let's try and figure out what that transformation might be. Well, here's what we're going to do. We're going to break it down into a couple of parts, and we're going to go joint by joint until we figure out what this transformation is. Okay. So we're going to start out with something a little bit special. Let me just copy and paste this. Copy. Scroll down here. And paste. Nice. All right. Let me get some of this stuff out of our way.
Could you also slide it up?
Yeah, sure. Is that good? Okay, perfect. All right. Let me erase these. All right. So let's say that our robot is starting out in its reference configuration. All right. So start out in reference. And what this means is that none of these angles have actually, moved yet. None of the joints have moved. They're all just staying still in their basic configuration. Okay. So theta 1 equals 0, theta 2 equals 0, theta 3 equals 0. All right. Robot hasn't gone anywhere. Yeah.
Sorry. So if we do a right transformation on a point,
Mhm.
it is like the orientation aspect doesn't matter, right? The P is the thing that matters.
So what the rotation matrix will do is that it changes the orientation in the sense that it's changing the basis vectors that we're representing that point to. So first we're changing the basis vectors, then after that we're adding on that translation.
Oh, I see.
Yeah. So we have to change it to be aligned with these new vectors first, and then we translate it once it's in that direction. All right. Nice. Okay, cool. So let's try and think about what we could do at this point, right? So we know that all up, what we want to do is we want to figure out what this point is in the spatial frame after this robot has been rotated around all these different joints by some arbitrary set of angles. Okay. So where do we begin? Well, we could start out by transforming PT into the spatial frame. And why do we want to do this? Well, in the reference configuration, this is something that's pretty easy for us to do, right? All we need to do is just find the rotation matrix between these two, like RST, that's taking us between these two. And then we just need to find the translation between these two, right? PST. And this is something, that we've done in our homeworks before. It just comes down to finding like a simple change of orientation matrix and then finding a simple translation, right? So this GST of 0, what that's going to be is the transformation between S and T in the reference configuration. Okay, so the robot's standing still. How do I get from here over to here? What's that look like? So that's what this GST is doing. So if we multiply GST of 0 by PT, what does that give us? Well, what that gives us is the following. So it gives us, so it gives us an early version of PS, but it's not PS when we've moved all of these angles, right? It's PS where each angle is equal to 0, all right? So this equals PS of 0, 0, 0. All right, so we now have it in the spatial frame. But all the angles are still 0. Okay, so this is the first step of our problem. We're just going to bring it into the spatial frame because we know that ultimately that's where we want it to be. But right now, we still haven't moved any of the joints, so we make that transformation nice and easy for us. Okay, so where do we go from here? What are we going to do? Copy this picture. And let's talk about our next step. Oh, sorry, I just erased those because they were in the way of the. Yeah. So let me just rewrite those. So we have RST of 0 and PST 0 between these steps. Sure. All right. So here's what we're going to do now. We're going to start out by rotating this furthest out joint by some arbitrary angle theta 3. All right. And I'll talk about why we're doing it from the backwards back in front in just a sec. So we've now rotated our arm by angle theta 3 over here. Okay. So now maybe our point is sitting like somewhere over here instead. All right. PT. So since PT is staying within this frozen frame, it's still the same vector from within frame T. But now, since we're applying this rotation by this first joint, it's going to look a little bit different from PS. Okay. So let's see what that looks like. So we know that we can find a twist. Twist I3 corresponding to joint 3, right? And that twist will help us describe the motion of joint 3. And what's important is that Xi3 is in the spatial frame. All right, so we can always find this twist in the spatial frame. So that means that when we do e to the xi hat 3, times theta 3, and we apply that to some point in the spatial frame, that will be equivalent to a rotation around this joint theta 3 in the spatial frame. Okay. So let's think about how that matters and how that ties into what we just did above. So now, if we go ahead and we do the following transformation, e to the xi hat 3 theta 3 times gst of 0 times pt, what is that going to give us? Well, now we know that this is pt in the spatial frame in the reference config, right? And this was that point that we talked about, which was ps 0, 0, 0. But what does e to the xi hat 3 theta 3 do? 3. Well, it rotates in frame S about your axis of rotation omega 3 by angle theta 3. Okay. So now we're going ahead and we're rotating this point in the spatial frame by this angle theta 3. So we know that this is going to be equal to p 0, 0, and theta 3. Okay. So now we've taken that point, we've rotated it by theta 3, and it's in the spatial frame. Okay. So that's going to be giving us this point over here. All right. So that's going to be ps of 0, 0, and theta 3. All right. So what's important to note in this case is that why go from outside in? Right? Like, why do we start all the way over here with this furthest out joint? Why is that something that we want to do? Okay. So here's why we want to do that. If we start with theta 1, if we start with theta 1, with like xi 1 and theta 1, and we move about this axis first, that's going to move the entire rest of the robot arm, right? So if we start out by moving this, then this guy is going to move over here, right? We're going to end up with that over there. And then this other arm will also be moving over there. And that's going to throw off our calculation of the twist for those arms, right? So if we start by multiplying by the theta 1, we're not going to be able to use our reference frame values for the twists of these other joints. Yeah.
Clarification. Does PT change when we move out of the robot arm?
No, so since that frame, the T frame is staying fixed to that robot arm, PT will stay the same from within that frame.
Are we saying that the frame T was made with respect to PT?
Yeah, so PT is with respect to frame T. So if this is like the z-axis of my moving frame over here, and this is the point PT that I'm concerned about, when I'm moving this, it's still at the same height from within that frame. It's just from the spatial frame that it appears different. Does that make sense? Or
So the position of PT transfer.
so the position of PT in the spatial frame will change. So like if this is my point right here, right? Currently, this is its position in the spatial frame, right? And this is its position in the tool frame. So now if I go over here, its position in the tool frame is still that, but now it's all the way over here in the spatial frame instead of being over there.
Is there a reason why we don't consider PT as our end effector instead of, or is it essentially the end effector?
Yeah, so it can be. So we just chose PT to be like any arbitrary point in this tool frame. So we could just choose it to be like the position of our end effector if we want. Like we could choose it to be 0, 0, 0 within our tool frame. But we just want to keep it arbitrary in this case.
So because it's part of the tool frame, when we write it as P sub T, that means that that vector's value doesn't change.
Right.
Because it's with respect to T.
Yeah, it's with respect to T, which is just moving with the robot.
Got it.
Yeah.
Thank you.
Sure. Yeah.
I'm sorry, I keep on bringing it back.
Sure.
I just like, there's just like something I just can't get over.
Okay.
So we had our Zyre rating.
Right.
That started with Zyre 1. Always Zyre 6.
Sure.
Like, so the actual formula is we're going in reverse, right?
Yeah.
But like, I don't know, I guess I'm confused, like, because we do on the code, at least for like when I'm reading it, it's like going backwards from how we actually are doing it.
Yeah, yeah.
Is that how it's actually read? So like, even though we're going backwards in reverse, like we can't, like, once it's all said and done, if we already have all the values,
Right.
we can just read it linearly from like left to right.
Yeah, so if you have like e to the xi hat 1 theta 1 all the way through like e to the xi hat n theta n, We always read it starting from here and then going backwards in this direction, because when we're multiplying points by these matrices, we always multiply them over here, right? So first we're doing this transformation, and then we're moving on to like whatever e to the psi hat n minus 1, like theta n minus 1 over there. And then we're applying like this to that, and so on and so forth. And we keep moving left that direction. So since we start out by multiplying this point on the right, we make our way left as we perform these matrix multiplications.
I'll have to ask later.
Okay, cool.
I think he's referring to the, if it's like commutative.
Oh,
Well, not,
Not really. It's just like, cause like, it's like our live array started with 1, and we were doing, we called math on like that with betas.
Right.
Right, so like if the betas are transposed, those are arrays. then-
like you have like
So like
xi1,
that's
xi2.
one. But like then we use the exponent, the pi xm.
Was it like something like that you said, or?
Yeah, but like, I mean, like, the way that Python reads it doesn't really matter. It's transpose time.
Okay.
But this is like the multiplication.
Okay.
We did it from like I1 to I6, and then at the end we multiplied it by g is 0.
Oh, yeah.
It's
So,
weird if, like, for me, like, when I'm reading the code, I'm reading it from like left to right. Like, why would we
Right,
do
right.
I6 first?
Yeah.
First like that.
yeah, so matrix multiplication is associative, right? So that means that we could really like block it out in any order that we want. Like we could, if we have like A times B times C, like we could first do A times B and then do that times C. Or we could do like B times C and then that times A. And then that'll give us the same result. So it's because of that like associativity of matrix multiplication that you could sort of read it either way.
So then I which one,
Right.
which time is.
Yeah, like you could think of it that way if you. Yeah. Sure. Okay, cool. So now what we've done is we've rotated about this first joint, right? So we've gone to an arbitrary theta 3. That's great. Now we need to do the other two angles, okay? So, yeah, let me just finish talking about why we do from the outside in. So if we start out by rotating about this theta 3 joint right here, right? We know that we can take that twist in the reference configuration, because when we start to rotate by theta 3, still nothing's changed yet, right? And when we rotate by theta 3 to this new angle, does it affect the joints before it? No, right? If we move theta 3, that's totally independent of theta 2 because it's further down the line. So that means that when we pick out the twist, xi2 for theta 2, that twist will still be the same twist from the reference configuration, all right? And then similarly, like when we move xi2 to some position and we go to the case of xi1, it still won't affect that. And when we go all the way over to like xi1 over there, that will also be the same twist as the reference configuration. Okay, so we just go from the outside in so that these further out rotations don't affect the further in. All right, this allows us to really just read off the twists just from our initial reference configuration instead of having them all depend on each other, which is a really like tricky way of looking at the problem. Okay.
You can just write it like one thing.
Yeah, sure. So outside in. All right. So why? If we start rotating from the outside, from furthest out joints, those rotations don't affect joints further in. So then all the twists we can use is then just the same as the reference configuration. Because those earlier twists, or those earlier joints still haven't moved, so they're still essentially in the reference configurations. All right, how do we feel about that? Okay, so let's talk about the next joint. So let me go ahead and paste this picture back in here, and we'll talk about what happens when we move the next one. All right. So we've already gone ahead and we moved that outside joint. Now we're going to go ahead and move in the theta 2 direction. So let's say that theta 2 is now rotating to this point over here. connecting to theta 3. We already rotated theta 3, right? So then that'll now be some other point over here. Now point P is maybe going to be like up here. So that's like point PT. All right. So remember, we already decided this angle of rotation was some theta 3. This angle of rotation will be some theta 2. All right. And it's in this case that we sort of see how that's, outside in formation works, right? Like when we changed this theta 3, theta 2 was still in the same position, so we could use its original twist, okay? So when we move theta 3, theta 2 joint is still in its original position. Okay, so can use the original joint 2 twist. Okay. So now when we're looking at the motion of joint 2, we know that this is just another one of those basic joints that we talked about, right? So we can find a twist Xi2 for the motion of joint 2. Okay, and what's the transformation of moving by some amount theta 2 around this joint Xi2? Well, we know that that's just going to be the exponential once again. All right, so transformation of moving joint 2. That's going to be e to the Xi2 hat times theta 2. Okay, so now what I'm going to do is I'm going to solve for this point over here, which is our new PT. This is going to be PT not only after we remove the first joint, but after we remove the second joint as well. Right, so it's going to be PS. This is going to be in the spatial frame of 0 because we still haven't moved that first joint. Theta 2 because we've now moved the second joint, and theta 3. All right, so what's that going to look like? All we need to do now is just multiply on this e to the xi hat 2 theta 2. So PS of 0, theta 2, theta 3 equals e to the xi hat 2, theta 2, e to the xi hat 3, theta 3, GST of 0 times our point PT. All right, so let me just summarize what each of these terms are doing, because I feel like this is starting to get like a lot to keep track of, right? So our first term over here, we're taking PT, converting it to the spatial frame. Convert to spatial frame. And the reference configuration. All right, so great. We have it in our spatial frame in the reference configuration. I know the distance from here to here. All right, now the next thing I'm going to do is I'm going to rotate joint 3. All right, so rotate joint 3. Joint 3. All right, so that's going to move that point in the reference configuration a little bit. So now, say I'm rotating joint 3, my distance from here to here has now changed because I've applied this transformation e to the xi3 theta 3. Okay, so this changes our point in the spatial frame. So rotates the point in spatial frame. All right, so we've done that rotation. Now we're going to just apply one more for the next subjoint. Okay, so now what I'm going to do is I'm going to take this rotating point and I'm going to rotate a little bit more. I'm going to move my second joint. All right, so now we've moved over here instead because I moved the second joint. Right? So then this means apply rotation about joint 2. Okay, so far we're taking a transformation from this arm where both the third joint and the second joint have moved, and we're taking that into the spatial frame. All right, do we have any questions about what we've done so far? Right here. Okay. All right, cool. And finally, we just have the third joint. First joint. Going backwards is a little confusing. So first joint. What is that first joint going to look like? This is really just going to be the same thing that we've done so far, right? So now, what we're going to do is we're just going to take everything that we've done over here, and then you're just going to move back the first joint instead. And one of these. And let's say, just for this I'm mixing it up, that we're going to rotate the other direction. And so theta 1 is going to take us over to our second joint, which we've rotated at some angle. So maybe that. It's going to be our angle theta 2. And then that attaches to our third joint, which we know we can rotate it at some angle theta 3. Right? And there's our arm over there. Okay. So that's our axis, that's our axis, that's our axis. Theta 2 and theta 3. And finally, we have our point all the way over here. Okay. So we know that a transformation about the final joint, we can find a twist xi3 or xi1. Right, twist xi1. Just like we did with all the others. And remember, since xi1 is all the way in, those rotations about those other joints have no effect on xi1. So that twist is going to be the same as it originally was. Okay? So find the twist xi1. And now we know that the transformation e to xi1 theta 1 is equal to moving by theta 1 around joint 1. Okay? So let's apply this transformation and let's see what we finally get. So we're going to end up with PS now of theta 1, theta 2, and theta 3. Right? This is our all-up transformation. We're now going from our tool frame into our spatial frame after we've moved all of these angles. And that's going to equal e to the xi hat 1, theta 1, e to the xi hat 2, theta 2, e to the xi hat 3, theta 3, GST of 0 times our original point PT. All right. So what we found here is we have mapped from an arbitrary point PT in the tool frame to its representation in the spatial frame after moving by theta 1, theta 2, and theta 3. And just remember, these theta 1, theta 2, theta 3, we didn't decide any values for these, right? The same for the twists. So all the twists we chose were totally arbitrary. All we required was just that they were valid twists. They could either be rotations like the drawn here, they could be prismatic, they could be screw joints, and same for all of these different thetas, right? They could be angles or they could be distances that we're moving. So because of this map that we found is a general transformation between our tool frame and our spatial frame for any joint configuration and any set of types of joints. Okay. So what we've done is we found a map. We were looking for. Great. So remember, we had said all the way at the start that we were looking for this map GST of theta that would take us from this point of the tool frame to this point of the spatial frame for any set of angles. Okay. So we found that PS, like theta 1, theta 2, and theta 3 was equal to this GST of theta times PT, right? This GST of theta must be this guy that we solved for up here, right? So for this manipulator, GST of theta equals e to the xi1 hat theta 1, e to the xi2 hat theta 2, e to the xi3 hat theta 3, GST of 0. Okay. So this was the map that was taking us from our tool frame to our spatial frame for any set of angles. All right. So this is called the product of exponentials. Product of exponentials. Okay. So I realize that was a lot. So if you guys have any questions, please, do let me know. Yes.
Last time,
Sure.
so the PS, so on the, before we had the three angles, we had the 0 in the theta 2 theta 3. How come the 0 drops off from the last iteration? Like, or is that?
Oh, so we have this like GST of 0 here is.
Inside of the PS, like inside of the.
Oh, I see. Yeah.
Like, does it matter that like I don't know, I just like a thing of like notation.
Sure, yeah. So the thing is that all of those zeros disappeared since we're replacing those zeros like with the actual angles that we're referring to.
Oh.
Yeah, so each of those zeros just refer to,
For the,
yeah,
dots, okay.
yeah, exactly. Yeah. So the first zero was like theta 1, and then theta 2, and theta 3, and in the reference configuration, they're all zero. Yeah. So we started turning by these angles. Yeah, great question. Yeah. Right. Do we have any other questions today? Or how do we feel about this? Yes.
Yeah, just off the top of my head, but did we ever go over like what the exponential actually gets you? Kind of go back.
Oh, yeah. So I think there's a formula for it for the two cases. So one is the rotational case, and one is the prismatic case. So if you have like a twist like xi equals v omega, what you're going to get in the rotational case is e to the omega hat theta, and then I think it's I minus e to the omega hat theta, omega hat v minus omega transpose v theta. I believe that's what it is.
Is this Rodriguez?
So this is like an equivalent of Rodriguez's formula for Fe3. Oh yeah, I'm sorry. E to the xi hat theta is equal to that. So in the same way that we were able to figure out Rodriguez's formula for e to the omega hat theta, which gave us a closed form for this exponential, we're able to do the same thing for the xi hat. But our translation right here, this is our rotation. Our translation just ends up being a lot more complex because we have this combined rotational and translational motion. But in the case of a prismatic joint, where we have xi equals v and 0, it actually ends up being quite intuitive. So in this case, e to the xi hat theta is equal to the 3x3 identity matrix, which starts I3, and it's a v times this we translate minus 0, 1. So all this means is that we translate theta. Translate theta in direction v, right? This means we don't rotate at all since it's the identity. Yeah. Yeah, I'm sorry. Yeah, just to clarify, this is like a 4x4 matrix since this is like a 3x3 rotation matrix right here, and this is a translation in R3. So like this is one of those RP01 matrices. So I'm just trying to like figure out the components of that.
Yeah, I guess, so I know that we have the R.
Sure. Yeah. So that's if we know the twist for our robot joint. But you know, we want to figure out like what the action of that twist actually is. So if we want to figure out for like an arbitrary twist, so for a twist and an angle theta, like what translation does it give us? What is the transformation G? We want to go straight from that twist into the transformation. That's when we would use this formula up here to figure out what the rotation associated with that twist is and what the translation associated with that twist is. So this right here is this like P. So that is the same as that. And yeah, like this is the same as this. All right. So do we have any questions about this whole product of exponentials formula or like what we talked about just down here? You know, it's definitely a lot to take in all at once. Definitely switch some things into our time. Yeah.
We won't be required to like be able
No.
to.
Yeah, so this is only something you'll ever really do in like NumPy or something like that. So don't compute by hand.
Open Python.
Do we have to do the crosswalks? Right? Like it wouldn't.
Yeah, so in the case of the cross products, you can, or you probably will have to do them by hand. But a kind of like nice trick for cross products, if you like forget that determinant formula, is like if you use like a vector v1, v2, v3, and you're taking the cross product with like w1, w2, w3. That's equal to, you could essentially just like distribute the cross product among these different components. So it's like equal to v1, w1, times like the cross product of like those two. So if I just write this out like in this form instead. So like if you know v1, they call it the I hat direction plus v2 j hat plus v3 k hat crossed with w1 in I hat plus w2 in j hat plus w3 in the k hat. You can essentially just like distribute these over here and then like add up all of those different sums of distributing, and then to figure out like what this I hat, j hat, and k hat are, you can just use the right hand rule directly to compute them. So you can always try it that way if you like forget that determinant formula. That can occasionally be quicker if they give you like vectors with a lot of zeros in them, because a lot of these terms will just drop out. Yeah, yeah. Right. Yeah, but I would recommend just using that determinant if you're not super sure otherwise. Yeah. You will probably need to use it for doing like the negative omega cross Q's and stuff. And then for the direction of rotation, that like second right hand rule.
Yes, that was so hard.
So if you're trying to figure out like the direction of positive rotation about an axis, say like this is your axis and it's pointing upwards, you put your thumb in the direction of the axis, and the direction your fingers curl is the direction of positive rotation. Yeah. All right. So we have around 10 minutes left. Do you guys want to do an example now? And we'll see how that goes, or otherwise we can just do questions. You know, I haven't reviewed any material for inverse kinematics since last year. So, all right, I'll have it ready by next week. Yeah, and then also, yes, yeah. So the notes for the screw motion and for kinematics will hopefully be up by later tonight. They were just taking a little bit longer than I expected, which is why they're not out yet. But yeah, check those out if you want like a more in-depth treatment of some of this stuff. Yeah. All right. Oh, great.
Yeah.
I thought the colors would be nice. Awesome. Okay, so I guess we could do like a super simple example here.
Are you gonna distribute your notes of the?
Yeah. I'll just put them on the announcement.
You have to go 3D.
Yeah.
Go 3D.
Sure. Yeah. Okay, cool. So we could just try out this problem real quick. We'll see how it goes. We're almost out of time, but I think we could probably make it. L2. All right, cool. So here's what we're gonna do. First of all, when I see like one of these kinematics problems, I want to find forward kinematics. Forward kinematics. What do we do? So first, it might be nice to lay out the product of exponentials. Just to see what we need to solve for in this case. Okay. So we know just using the product of exponentials formula GST of theta will be e to the I hat 1, theta 1, e to the I hat 2, theta 2, and e to the I hat 3, theta 3 times GST as 0. Okay, that's just following that same formula that we derived earlier in a big long-handed process. So what do we not know? Okay, so we're given this theta 1, theta 2, and theta 3. What do we need to find? Well, we have, these xi's unknown, so we don't know what xi1, xi2, or xi3 are. Okay, we also don't know what gst of 0 is. Okay, so we got to start out by deriving these twists and deriving this transformation. And then once we have those, all we need to do is just go ahead, plug into that product of exponentials formula, and we'll be at our final answer. Now, just something to note is that once you find these twists and you're working on a problem on your homework or your exam, you're pretty much done. Okay, so we're not actually expecting you to perform these matrix multiplications, with those horrible matrices that we wrote out up here, as I minus e zero that data. You won't need to deal with that stuff. Yeah. So thankfully, all you need to do is just solve for these twists, solve for your GST of 0. You'll be golden. Okay. So let's start out by solving for GST of 0. Okay, so remember, this is going to be in our reference configuration. So it's going to be like in this picture right here, where all of our angles are still at 0, just pointing straight out. All right. So we know it's going to be of the form RST of 0, PST of 0, and a 0 and a 1 underneath. Right? This is just that format for SE3. All right. So let me just draw out these reference frames in more detail so we can get a picture for what is going on. So something like this, and then we have another reference frame over here. Okay, so that's our tool frame, and this is our spatial frame. So we have xs, yx, zs. But when we look at our picture up here, the natural orientation of our tool frame is actually different, right? They've given us some different order for the vectors. It's not very nice. So we have an xs over here and a ys over there. So this is something that's going to happen in a lot of these problems, right? Even though we haven't actually rotated yet, the tool frame and the spatial frame might have a different natural orientation, okay? So that means that RST is not necessarily going to be the identity matrix, okay?
Just a question.
Yeah.
Is that still XS, YS, and YT?
Oh, shoot, I'm so sorry. Yeah. So that's going to be T in that case. ZT, XT, and YT. Okay, so we can start out just by looking for this rotation matrix, and then we get that translation in this case. Okay, so our rotation matrix, RST, well, we can figure it out by looking at the different basis vectors and what they look like from the frames, right? So our first column is going to be XT as seen from frame S. Our second column is YT as seen from frame S. And finally, ZT as seen from frame S. Okay. So when we look at XT from frame S's perspective, it looks like it's just pointing in the Y direction, right? So then our first column is going to be 0, 1, 0. Now what about YT? YT is pointing in the direction of Z. Okay, so 0, 0, 1. And finally, what about ZT? ZT is pointing in the direction of X in frame S. So then 1, 0, 0. Okay, that gives us our RST of 0 right there. Okay, so just when it's frozen in space, we just check out the orientation, look at where these basis vectors are pointing, and we can figure out our rotation matrix just by that. All right, so what about our translation? Well, it looks like we're going over by L1 and L2 in our Y direction, right, with respect to our Y right there. And we're going up by L0 in Z direction. All right, so this is when we're in a reference configuration. So what does that look like? What sort of translation does that give us between this frame and the reference configuration? Well, all that that's going to be is the following vector. So you know that we are going over, like in the Y direction over here. That's L1 plus L2 between those two frames. And then in this direction up here, it's just going to be L0. All right. So EST of 0. First, we could just shift over in the Y, like 0, L1 plus L2. Right? That'll take us over where we need to be over there. And then we can just add on where we need to be in the Z direction. Right? So we need to shift up by L0. And that gives us our PST of 0, L1 plus L2, and L0. Okay, so all up when we go ahead and we plug this into our GST of 0, which had that like RP01 format, which is what we're going to get. So sorry if I'm going a little bit fast. I just want to do one of the twists, and then yeah, I think we should be good. 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, L1 plus L2, L0, 0, 0, 0, and a 1. Okay. So all up, this is what our GST of 0 is going to be. All right. So once we have this, we can move on to solving for our twists. So going to solve for the twist. All right. And just as an exercise right here, I'm just going to solve for the twist of joint 2, just because I think that might be the trickier one out of these. So here's what I'm going to do. I'm going to take this axis of joint 2, and I'm just going to trace it down all the way. All right. And that way, we're going to figure out what a good point on this axis will be. Okay. So looking at this joint, we see that when this axis goes all the way down, right, it's not actually passing through the origin. Okay. So when we're picking a point on this axis, we can't choose the origin, right? We can't choose Q equals 0, 0, 0. But maybe the next best thing is right over here. Okay? That looks like a good point on the axis because, you know, at least 2 of the other coordinates are 0. That's pretty good. Okay. So let's go ahead and solve for the twist. Okay. So looking back at our diagram, what type of twist is this going to be? Well, this is a revolute joint, right? It's just twisting about that axis, just rotate it. Okay. So this is going to be of the form negative omega cross Q and omega. Okay. So we see that omega from the picture is just going upwards in the z direction, right? So omega 0, 0, 1. Now what about our point Q? Well, let's just go ahead and check out what that was. Remember, this omega and this point Q, these are going to be represented in the spatial frame. Okay. So when we take a look at this point Q that we chose, we see that it's just a distance L1 along the y-axis of the spatial frame. All right. So we just trace along this axis until we find a convenient point. We choose this point Q, which is 0, L1, 0. All right. So we have Q equals 0, L1, and 0. Okay, great. So then we perform our cross product, negative omega cross Q equals 0, 0, negative 1, crossed with 0, L1, 0. And you could go ahead and calculate out the cross product for that, and you should end up getting L1, 0, 0 in this case. Okay. So we have our negative omega plus Q. We have our omega. And all that we need to do is just stack them together and finish our twist. Right. Then we get Xi2 L1, 0, 0. So that takes care of our negative omega cross Q. And then 0, 0, 1. Okay. So that will take care of our omega. And that gives us our twist, our joint 2. Okay. So just make sure when you're doing these, make sure that you actually sketch out where your axis omega is going. So that way you won't pick a point like the origin by accident. And that way you can sort of visualize what might be a convenient point to pick that's still on the axis. So that's what I would recommend doing when you encounter these sorts of problems. But yeah, other than that, the other ones, you really just follow the same procedure for solving for this. Yeah, I'll stick around if you guys have any questions, because it looks like there's no one after us. Yeah.